The topic is very relevant to what we have learned, and that is the simple applications. And for this topic, vibration oscillations, and there's one set of the homework, okay? And I think that is the one due on this coming Friday. So very likely today you can go back to there and right away to do everything. And for that particular homework, I will specify what kind of information. And for my solution is this: I simply implement the equation into the spreadsheet, into the Excel spreadsheet. And I put the M, C, K, and omega as the parameters. So that means every time I have the similar problem, I simply go to my Excel spreadsheet, I change the parameters, and right away I got the numbers. Okay, so that's what I did. And I will give you more details. So the vibration isolation, the concept is this. If you would imagine this is a machine, okay? For example, the CNC machine in the machine shop. And to be, for our CNC machine, that has been, I think Eric Johansson and Joe has been doing quite a bit, spend time over the summertime and to get the machine ready when they move from the old machine shop to the new one. In particular, I believe they not only set up the facilities like the electricity to get that work, but also it's kind of the mounting the installations. And one of the installations including is the this kind of called the resilient members. That is a term by our textbook. Basically, this is the isolation design. And in principle, that kind of this elastic and damping material basically in principle can be simulated by a single spring plus a single dampers, okay, the simplest way. So under these approximations, we will be able to use what we learned in these chapters. So under that kind of the modeling, basically that is a chunk of the machine, and we approximate these vibration absorbers in terms of the single spring and the single damping. Of course, if necessary, once we approaching into, say, more chapters, more information, you can always simulate the absorber into more complicated combination of the spring and damper. Okay, but in concept, we can do this. And again, when machine is operating by its own machine operation, it's going to induce the excitations. So that excitation here, we're assuming, for simplicity, we're assuming that is in cosine, oscillation of cosine with a magnitude f0. Okay, so basically, if we look at this system, that is exactly what we've been dealing with in these chapters. Okay. And now with this model in mind, we simply look into the applications. And this is a very practical applications. This page is a summary. So using this as a model, and we know that for the steady state response, we have this form, okay? And this is called the steady state amplitude or steady state magnitude. And that is the equation we know about this. This is the phase angle. So basically, in my Excel spreadsheet, I simply implement this equation and these equations, and with 4 parameters: N, C, K, F now, and omega 5. Okay. So basically, I have that one implemented, and then for every single problem in the homework, I simply put into the input those parameters, and right away the numbers coming up. Okay. And so that is what we have known. And so for the design of the vibration isolations, we focus on 2 things. The first thing is about the protection of the ground. So that means in terms of the first things in the vibration isolation, that means in terms of vibration isolation, that means we try to design and select appropriate materials to do something. And this material, how to choose and how to design, basically we pick the K and C's and such that we can achieve some the design goals. The first one is on the protection of the foundation or the base. And by reducing the force being transmitted to the ground. Okay, when machine is operating, they're going to produce force. And how much is a force? You can see if this is a mass block or machine by itself. When it is under the degree of freedom, this vibrating. So here, due to this displacement of the mass block, this is a spring force being produced. And this is the damping force being produced. Those are the two forces pertaining to this model that are going to translate to the ground. So this is the ground, and that's the action reactions. Okay, to the ground, basically these are action reactions. So basically here the total force being transmitted to the ground equal to Kx plus Cx dot. Okay. So the first design aspect of the vibration isolation is to minimize this force. That means our goal is to minimize this quantity. And how to do that one, and we can do a little bit study here. So we want to know how much the force being transmitted to the ground. With that information at first, then we will be able to do the minimizations. Okay, so the first step is to we try to formulate what is the force transmissions, and at the steady state, and so this is the magnitude of the force, and that is per our formulations there. So that is the spring force plus the damping force, and we plug in at the steady state here. And that one basically is this, and you can see we introduce the xt equal to this one, so we simply take the derivative. So once we introduce the k times x, this is the steady state force, okay? Again, here we assume the steady state response is like this. So simply this, the first term representing is a kx, okay? Then the second term representing is a cx dot. When you look at this carefully, x dot, by operating on this form, cosine after derivative become negative sign. So that reason why you come up with a negative here. Okay, and c multiply, once we have the sign derivative, then this have a omega. So basically the second term representing simply is this term. Good? Okay. So that is the time domain representation of the total force being transmitted to the ground. And furthermore, for the optimizations, we want to minimize the magnitude of the force. So basically here, the second step is we simply calculate the magnitude of this term. So the magnitude of this term, everyone should already know. Basically, that is the coefficients of the cosine. These are coefficient of sine. We simply take the square of those coefficients, take the square root. That's just like this. Okay, so the magnitude of the force is expressed by this. Okay, and what is x? X has been known earlier, that is this form. So basically in total, we know that if we plug in the information of the x is the steady state response of the system, and simply multiply with this one, so we can rearrange. So that means the ratio of the force being transmitted to the ground to the magnitude of the given loading. What is F now? F now is the magnitude of the given loading. So this ratio simply is in terms of this form. And this form, we can using the similar the techniques that can be expressed in terms of the R. R is the frequency ratio, and zeta, that is the damping coefficient. Damping ratio, sorry. Okay. So this graph will be the second new thing, and this will be the first time appear here. This graph simply documents these complicated equations, okay? And this graph is defined by this ratio, and this ratio is called the force transmissibility, and that is the answer. So that is our next page here. I summarize in the next page here. So this page basically summarizes the first design aspect of the vibration isolations, and that means our focus is on the the determination of how much force being transmitted to the ground. Okay, again, this ratio, and if you like, you can put a note on the numerator here. Ft representing is the magnitude of the force being transmitted to the ground. F now is the magnitude of the given harmonic excitations. Okay, and that one can be exact expression is by this term, and this term basically we can look graphically just like this. Okay. If you compare this graph carefully with the previous one we learned last week, that look different. Okay, look different. So from this point onward, if you really like to prepare a cheat sheet for yourself, and my suggestion is this: on a separate, you simply put the graph, you copy and paste the graph, and then to the side of the graph you denote that is the say magnitude magnification ratio. Or that is called the transmissibility, this one, because different graph has the different meaning, okay? And for this one, we define as a transmissibility, or we define this ratio is called the transmissibility, or different name is called the transmission ratio, and even another name called the force transmissibility, and those terms appear in our textbook and in other textbooks. And I prefer is using this term force transmissibility, and which is also used in our homework, because that one tell clear that is about the ratio between the force and transmitted. Okay. Sometimes for this one, who knows? For God's sake, who knows what's that? Okay. Again, another thing, again, I want to reinforce, if you really want to prepare the cheat sheet, and you can copy and paste this figure and put a note, and that is called the force transmissibility, okay? And this is the second figures we've seen, okay? This is the exact equations here, and many times as an engineer, I don't think that would be hurt if you only look at the graph and do approximations. For example, say, for my design, and say I pick the R equal to say at the resonance, and for damping ratio equal to 0.5, then the force transmissibility at this point is about 1.4 or 1.38, approximate 1.4. And in terms of this design, and say in your test or not doing the homework, we are accepting is the accurate calculation, but in the test, if you like to use the graph and approximate, say that ratio is about 1.38, I take it. Okay. Otherwise, you can plug into this equation to do the detailed calculation either way. Okay. And so that's the reason why I'm saying you can put this kind of graph in your cheat sheet to help yourself and do some kind of quick estimations, but not using this one for homework, please, because homework for the blackboard, and I accepting is more accurate the numbers, because the tolerance sometimes is, I think most of the time is less than 3% of the whole answers. Okay. Okay. On the other side, and this is the exact expressions, and sometimes for small damping ratio, this one can be approximated by simple forms, and these are approximations. Okay. So that's for your reference. And for the isolator, the vibration isolator design, basically most of the time our goal is to reduce, to minimize the force being transmitted. Okay, so that means in terms of the certain conditions, we're looking for the minimization problems. So we can look at this example here, and this is a whole solution process. And I think one homework question is related to this one, and we see how can we do it. So right now we have given is a mass, and that mass with a weight 85 newtons. So basically from 85 newtons, we will be able to know the mass of this one. Simply approximate about 8.5 kilogram. Okay, for this one. And now we know its operation in the working frequency is in between 25 to 35 hertz. So from hertz, we convert it into radian per second. So basically, that is the range of the operations. we go down. So now our goal is to have at least 80% of reduction in the force transmissibility of the machine. So we want to determine the diffractions to meet the goal. Basically, that simply word is we want to find out the spring constant and to meet the goal. So how to translate this information? 80% reduction in the transmission. 80% of the reduction in transmission. That means the transmitted force is 20%. Is 20% of the in the ratio. So that means in that the translation to here means this: the ratio between the transmitted force to the ratio to the given the amplitude. So this one, assuming that is ft equal to f now and say cosine omega t. Okay. So that f now is the magnitude being produced. And we wish that magnitude can be reduced by 80%. So that means this ratio, at least, is the maximum is 20%. 0.2. Starting from here, okay. And now starting from here, we know this one we plug into our previous example here, the equation that is this one. I couldn't memorize. So 1 plus 2 zeta r squared. 1 minus r squared plus 2 zeta r squared. Okay, we're plugging here and asking that number equal to 0.2 or less than or equal to 0.2. Okay, and and for this example, again, we pick up the damping ratio. For this one, it's an undamped system that gives us the good time. So that means for this case, the damping ratio is equal to 0. So this term can be simplified into this r squared minus 1 and taking the absolute value. Okay, and we don't know the r value is greater than 1 or less than 1. We simply keep the absolute value here. So this one is 0.2, and so graphically, I want to show what does that mean. So for that example, we know the working frequency omega is in 25 to 35 hertz. So that is some kind of the working range. Okay. So we look at this graph here, and we know that is a working range, and such that the numbers we're shooting for is 0.2. So let me make a line here. So if this graph is big enough, so this is 0.2. We're looking for that is our design level. And right now the damping ratio is equal to 0, so we focus ourselves on this curve. Let me highlight here. So this is our curve. Okay, so simply, our design is to have this is our design range. Okay, this is our design range because we want the transmission reduction at least 80%. So everything, all the value falling into here is good enough. So basically from here you can see this is the range, at least from here, this range will be working for our purpose. Be good? Okay, so graphically we can start from here. So now we can go back to continue the calculations. Okay, so so right now with this one, then we know the R value is equal to omega divided by omega n. So we know the omega range. So as long as we determine omega n, then we would know the range for R. Okay. So omega n is pretty straightforward. Omega n we can relate it to omega n is related to m over k, and we're looking for the amount of k. So right now the omega n is the numbers we're looking for. Okay. So keep those things in mind. Omega n with these informations, so we can go here first. So from this information, we can solve for r squared. So r squared, by solving these equations, that one r squared must be greater than 6. Okay. Do you know how to solve for this? We can do it. So for this one, we're asking this one is less than 0.2. Okay. So here when you solve for it, we have two possibilities. So when r is greater than 1, then basically is r squared minus 1 is less than 0.2. When r squared less than 1, then that means the 1 minus r squared less than 0.2. So we simply solve for the two conditions individually to find out these things. Okay. So for this one, you can see basically this one is 1 minus 0.2 less than r squared. This one, okay. So basically from here is r squared greater than 6. Okay. And this is our result. And here the condition is this one. So basically this is a legitimate solution. For this one, we can see this one is 1.2 greater than 1 minus r squared. So that means 5 less than 1 minus r squared. So do the things, r squared less than 1 minus 5. Well, and that's negative. So the only possible r is 0. So this one probably we don't consider. So that is the calculations. Okay. So once we have this one, then we know r squared must be greater than 6. And on the other side, r equal to this one. So we plug into here. And so right now we're proceeding to this. And so we can start from here. And because right now the let me do this. So r squared less than 6, that is what we found. And also we know r equal to omega n squared. Okay. So from here we because we're looking for k for this province, and we know the k equal to n times omega n squared. So basically, we're looking for omega n squared simply is looking for k. So here omega n is the unknown we're looking for here. So that means omega n squared. How to do it? Larger than omega n squared divided by 6. Yeah. Square 6. Okay.
Should we just get omega?
Omega? Yeah, thank you. Okay, and right now we are given omega is in 25 and 35 hertz. Okay, then we can convert it into the radian per second. Okay, so basically equivalent is omega n omega. And basically you multiply with 2 pi, that will get into the radian per second. Okay, so 25 multiplied with 2 pi, I think that one is 157.1. And how about 35 times 2 pi? 70 times pi, I think about 20. Maybe 241. Okay, quick calculations. So right now the omega is in this range, and omega n must be greater than this one. So we simply plug in the minimum value of the omega here. So that means here I plug in 157.1 divided by square 6, and that gives us omega n, the minimum value of omega n. Okay. So from here we can determine omega n, and on the other side, we want to determine the delta st. So from here, we determine omega n, then Anyone has any calculation can help you? Calculate what is this number? $64. Exactly? 0.09? 0.09, 0.1. Okay. So this one on the other side is K over M. Okay, so from here, the M equal to our mass, and we have a weight 85 newtons divided by 9.81. The gravity, the constant. So this is our mass. So from here we can determine K. You good? So once we determine K, then for this problem we want to know is the static deflection of this machine. And that static deflection of the machine, if you remember, that simply is equal to the magnitude of the given loading and divided by spring constant. And from here we can determine this one. And that is here. Good? And here I somehow using a different other, but any other would be similar to that one. Okay? Okay, any questions? If no, then we can proceed to the second design aspect. The second design aspect of the vibration oscillation is this. Again, we look at the same equation of the motion and we look at the same modeling. The vibration absorber be approximated by K and C. For the second design aspect is this. We wish the displacement of the machine can be minimum. And that it makes sense because sometimes in particular for CNC machine, not doing the project here, if you go to say in the future, if you have any chance to serve for a company that is working on aerospace or even the defense industry, and in certain components, machine components, the requirements of the precisions is down to the micron, the scale of the micron. The micron is how much? 1 micron equal to 10 to the minus 6 meters. Basically, 1 micron is 1/1000th of the human hairs, the diameters. Okay, and usually one bacteria. If you look at under the microscope, then usually their size is about the 10th of the micron. So kind of give you some ideas. So for that kind of scenario, definitely we wish the fabrications, the manufacturing of the components can be as precise as possible. If a machine under his own operation, say the spindle of the motors, induce the vibration, if that vibration causes the machine to vibrate too much, then by no means how skilled you are, you wouldn't be able to make the job. Okay, in particular, right now the CNC machine, they call it 5-axis CNC machine. They 5-axis, that means they have a 5-degree freedom. They can making the components from different angles, from different degree freedoms. Under that one, trust me, the machine can vibrate has been the issues. And in many mechanical engineering kind of discipline students, in particular I'm not familiar with the industry distribution in American, but in Asian, where in Taiwan I came from, that is a huge segregations of the industry. They basically on the CNC machine, and they've been trying to solve this kind of reducing the vibrations been wrong for a long time. Okay, for a couple of decades, and then the price of such machine depends on their capability of controlling, suppressing the vibrations. For our machine downstairs in machine shop, that's decent enough. Okay, and but want to go for the better one, then yeah, they have a better controller, active control. beyond our vibration. Here we're doing is a passive control. Okay, that means without any controllers, but they're doing something. So on the other side, the CNC machines from Germany, that is the top one, the class, the world class, the number one. Okay. So here I kind of give you some kind of ideas with this information you might looking for is the companies they're making the CNC machines. It have a big take of ME students for them. Okay. So for the second design aspect, we want to minimize the displacement. We want to minimize the steady state displacement of the machine block. Okay, so here we summarize again. This is the steady state response. And here, in particular, right now, the second design aspect, we want to minimize X. Okay, and that is design aspect. And what is X? And X is this one. Okay, or X is this one. This is the curve we've seen before. Okay, we've seen before. This one we define as the magnification factors. Okay, or otherwise we also call that the displacement transmissibility or amplitude ratio. Okay, so in the homework, I pick up this term, displacement transmissibility. Simply, that is our magnification factors. And for these vibration isolations, we simply want to minimize these numbers. Okay. In the similar process, once you know the damping ratio to minimize based upon the working range, you simply look at the curve. You can easily pick the point corresponding to which that will give you the good solutions. Okay, and this example is very straightforward, so I don't have examples, but this one basically summarizes our design oscillations. Good. Okay, so keep that in mind. Two aspects of the design. One is on the force transmissions, and the other one is on the displacement transmissions. Okay. Okay. Good.